this. Oh. Yeah. Okay, let's start with a rational number, which is like 65 by 18. No particular reason for choosing this number. This is simply because I worked this out already, so I chose this so that I don't run into complications. You can choose anything. So we are trying to expand it into continued fraction. So a visual way of seeing this is looking at a rectangle like this. So I'll just try to draw a rectangle. It may not be very perfect. So let's start with the rectangle. Say this is with size 65 and 18. So 65 by 18 rectangle. Now the problem is to cover this rectangle with squares. So as if you are tiling something. You want to cover this with square tiles. So want to cover with tiles. But tiles can vary in size. You don't have to have the tiles of same size. Tiles can vary. And but the only restriction is that they all have to be squares. So the obvious choice to start with would be this 18 cross 18 squares. Actually, this is the longer side should be more than 3 times 18. 3 times 18 is 54. But the drawing doesn't look like that. So it's slightly wrong. So anyway, so suppose, let me try to, these vertical lines are already tricky. So it should be 3. So just think about these as squares. These are actually quite bad. Difficulty drawing vertical lines. Yeah. So just assume that they are squares. They don't look like squares. Sorry about that, but then it is. So these are 18, 18, and 18. So a total of 54. So this gives you a total of 54. And it leaves 11 for this part. So this part, the part here, this is 18 cross 11. So this is 18 cross 11. So this is what the remaining part is. We have covered. Somebody wants to get admitted. It says in. Should I just click?
Admitted, sir.
Oh. Yeah, because I got a notification. So, yeah. So we already have 3 square tiles, 18 cross 18 tiles. So this is the first one, the second one, and the third one. And then the remaining portion is a rectangle of size 11 cross 18. So that's the remaining rectangle. Let's draw that. So let's draw that. Let's draw this. Say, okay, somebody has annotated inside this. So please don't annotate. I think you have to be careful with the mobile device. No, I can't remove this. So Okay, I guess this will remain. So what should I do? I go to the next page or something. Okay, so even if I go to next page, this will remain in the middle. So what should we do?
Is it any possible to delete the line, sir?
No, it's not. It's not working because I didn't do it.
So
So
stop sharing and share again. This is
okay,
save the file again.
okay. That's a good idea. Yeah. Oh, it's gone. I think whoever has done it by mistake has removed it. Yeah, it's fine. It's working. So yeah, I wanted to be on the same page because the numbers are good. Yeah. So let me draw the leftover rectangle. 11 cross 18 should be not so bad. So not so bad. Something like this. So this is now 18. This is now 18 and this is 11. And so as I said that we need to fill it with squares, but the size of the squares can vary. So now we have an 11, we can just fit in an 11 cross 11 square, not more than that. That's the largest square that can be inside this 18 cross 11. So let's put that. So suppose this is 11 cross 11. And then what I'm left with is 7. So this is a 7 cross 11. So 7 cross 11. So this is the remaining. So this I'm just mark it with this color that this is the remaining rectangle. Let me draw the remaining rectangle. So again, go back to this and let's draw this 7 cross 11. So that also is. No, let me keep the same color. So this is like something like this. So this is 7 cross 11. So this is 7, this is 11. And again, do the same thing. So 7 cross 7 is the largest square we can fit in. So let's fit that. So this is 7. So say 7 cross 7. And okay, let me write that. This is 11 cross 11. This is 7. This is 7 cross 7. And whatever remains is 4 cross 7. So we were still left with a rectangle. So this rectangle. So this is the remaining rectangle. We have to draw that again. Let me draw it. So this is 4 cross 7. So slightly elongated. So 4 cross 7 rectangle. So I'm always keeping the longer side horizontally. So it doesn't matter how I do it, but just this is the choice. This is what I'm choosing. So this is again a 4 cross 4. So you can't fit more than 4 cross 4. So let's draw it somewhat like this. So this is 4. This is 4 cross 4. And whatever remains is 3 cross 4. 3 cross 4. So 3 cross 4 remains. So this is my remaining rectangle. So we need to draw that again. Three cross 4. So 3, oh, sorry. 3 cross 4. And then again, we can fit a 3 cross 3. Oops, this is so bad. Yeah, so we can put a 3 cross 3. So this is 3 cross 3. And the remaining portion is just 1. So 1 cross 4. And once we have a 1 cross 4, then it is easy.
Sir, it's 1 cross 3.
1 cross 3. Sorry. Yeah, 1 cross 3. Absolutely. Thank you. 1 cross 3. Yeah, 1 cross 3. But erase this. This is too big. Yeah, thank you. So this is 1 cross 3. Yeah, so 1 cross 3, and now this is easy. So we can just put 1 cross 1 tile. So 3 tiles. Though even though the drawing is a bit bad, it doesn't do. But so these are 1 cross. Okay, let me just write 1 cross 1, 1 cross 1, and then 1 cross 1. So we have filled it up with squares. So what we have done, we started with the rational number, then went to this rectangle. So what we have done, let's see. So I don't want this to, yeah. So this was the number we started with, 65 by 18. So this is so this division simply means that 65 is 3 times 18 plus 11. That's what we use. So this is 3 plus 11 by 18. And what did we do here? So here what we have done is we have just written 18 as 11 plus 7 over 11. Right?
No,
and
this is 7. 18 by 11 equal to 1 plus.
Sorry. This is 1 plus, yeah, 1 plus.
That is 18 by 11 equal to.
18 by 11. 18 by 11 is 1 plus 7 by 11. And so these numbers are the number of squares. So these are the numbers of squares. So these are the number of squares. They are of various size, but so first one is 18 cross 18 squares, but these are number of squares. The integers appearing here are the number of squares. So the number of squares. So these are the number of tiles we are using. So similarly, here it is 7 by 11 is 1 plus 4 by 7. And then at the end, it is 7 by 4 is 1 plus 3 by 4. 1 plus 3 by 4. And then 3 by 4, so 4 by 3, sorry, 4 by 3 is written as 1 plus 1 over 3. 1 over 3. So these are the number of tiles we used. So the last one is actually, this is also the number of tiles. So this is, I would just write it as 3 cross 1. So that also the number of tiles. So we have used a total of 3, 1, then 1, then 1, and then 1, and then 3. So this is the number of tiles we used. And if we just see what we have done here is, just notice here that this is 3 plus 11 by 18, and then we took the reciprocal of 11 by 18. So it is 18 by 11. That is, and expressed is as 1 plus 7 by 11. And then this is again the reciprocal of the non-integral part, and this is 1 plus 4 by 7, and so on. Just we have done the same thing over and over. So if we all put this together, what we get is a continued fraction expansion. So let me just write it down. So this is 65 by 18 is the number we started with. We wrote it as 3 plus 11 by 18. Then we wrote 3 plus 1 by, so because we wrote this 18 by 11 as this 1 plus 7 by 11. So that is what is 1 plus 1 plus 7 by 11, and then subsequently we wrote 1 plus 1 by, so that is how we wrote this 7 by 11 is now 1 plus 4 by 7. So 1 plus 4 by 7, and this is 3 plus 1 over 1 plus 1 by 1 plus 1 by 1 plus 3 by 4. Yeah, 3 by 4. 3 plus 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 3. No. 1 plus 1 by, sorry, 1 plus 1 more. 1 plus 1 by 3. Hope this is correct. Yeah. And so this is what is a continued fraction, a finite continued fraction, and we would be denoting this by a square bracket 3 comma 1 comma. So we would just simply write, because all other things mean 1, so we are just going to write these things. So only these numbers matter. So the numerators are always going to be 1. So we just have to pick these numbers. Here we have 4 ones, but they are not necessarily 1. So we just need these numbers. So if we know these numbers, we can write this down. So 3, 1, 1, 1, 1, and then 3. So this is the continued fraction expansion of 65 by 18. That's the rational number we started with. So it is a rational number. So we would see that every rational number is going to have a finite expansion in this form. So we need to prove this. It's not entirely obvious from what we have done. So we have actually written down a kind of an algorithm which terminated, but we have to show that this is not an accident. Every time you start with a rational number, it's going to terminate. So we'll see that. But before that, I would like to talk about another example, which is not rational. Yeah. So we see that it becomes a bit cumbersome, and if it is not rational, then our this powering with square tiles with integer side, etc. doesn't work. So we would approach it in a slightly different way. So yeah, I mean, in fact, looking at the continued fraction, you know how many tiles you would require. So you simply have to add all these numbers which I circled. So sum total of all these numbers are the square tiles you require to cover the rectangle of side 65 cross 18. The squares vary in size, but they are all squares. Okay. So as I just mentioned, that let's try an irrational. So to have an easy irrational, of course, it's natural to start with square root of an integer. So here again, I have already calculated, so I'll start with that. I mean, things can become a bit cumbersome, so let me start with what I have already calculated. So which is square root of 7. Even for small number, it's quite complicated. So let me start with an example. So another example. So example of an irrational number. But at the moment, we won't venture into difficult irrational numbers. We just take a square root of an integer. So we would consider square root of 7. So this is what I'm going to work out. So what I want to do, now I know what I want to do. I want to write this number in this kind of form. So this exactly like these steps, like 1 by an integer plus 1 by an integer plus this kind of thing. So what is that? So we want to write it in this kind of form. So want to write it in the form, say A naught plus 1 plus 1 by 1 plus 1 by, oh sorry, these are not always 1. So this is 1 A1, A2, then A3 plus, so numerators are always going to be 1. So we want to do this kind of a thing. And and a priori, we don't know whether it's going to terminate or not. So since we haven't proved anything so far, the termination of the algorithm in last case is purely and could be purely and coincidence. We don't know. So let's see. So that's why we want to see it with an irrational number. So as you would imagine that it's expected to terminate for rational numbers, but irrational number, let's see what happens. So we want to want to write it like this, square root of 7 in this fashion, where this A0, A1, A2, A3 all are integers. So we want them to be integers.
So can we find a sequence, a rational sequence converges to this point? Is always possible.
Yeah, exactly. So that's a very good question, because one of the purpose of studying continued fraction is that we want to find explicit sequence of rational numbers converging to irrational numbers. It can be done for any irrational number. So square root of 7 is an easy irrational number, so to say. It's just a root of a quadratic equation. You can do it for much more difficult irrational numbers, even for what is called transcendental numbers. So we'll see that later. Yeah. So we need to develop some theory for that. So that's a very important application of continued fraction. Okay, so let's just start with this example to see what happens. Oh, I can see another line. Can you just remove this? No, I see another red line on the page. Which I can't erase. So somebody else has drawn it. Maybe I can. Oh, Gurushami, is it possible to this stop annotation by others?
I don't know, sir. Anyway, we will try.
Yeah, let me just see if I can do that. I am also a co-host, I guess.
Yes, sir. Yes, sir.
It may be, oh yeah, there is an option. Yeah, I can do that. Yeah. Oh, but in that case, somebody has to remove this one.
Participant, please, then please just delete the red line.
Right. Yeah, so if I think somebody must have done it unintentionally. So that's why it was, so the whoever has done it may not even know.
Yes, sir.
That's the problem, and the problem is that it continues to the next page. So every page will have this kind of a block. Gurushami, you can also see that, right?
Yes, sir.
Yeah, that is.
That is the problem.
That's a problem. Yeah, I didn't know actually how to stop. Now I see that there is an option, so I would do that. But can somebody remove this? Oh, okay. So I actually, yeah. So,
can you hear me?
You are audible, sir.
Yeah.
Sir, you're using a laptop or system. There is an option to annotating others.
Yeah, right. So I'm just doing that.
So others not use that annotation.
Right, exactly. So I have disabled that. Now I have disabled that. So what I would do, I would follow the previous suggestion. So just stop share and share again.
Yes, sir.
That's a good idea. Then this line.
Now no one can annoy with.
Okay.
You can you only can write anything.
Fine. This should work fine. So I'll just stop share and then share again.
Okay, sir.
Yeah, I think I'll just share again. Now the there were some chats actually. Oh yeah. So yeah, thanks for Mr. Ragul. So thanks for the suggestion. So that is what I'm doing. Yes. Share the screen again. Yeah.
Now it's okay, sir.
Yeah, now it is fine. Now it is fine. Yeah. So yeah, I didn't know this. So otherwise, I would have done it earlier. Okay. So okay, let's start with this quadrant. Okay. So this is what our idea is. We want to write it like this. So let's start by writing square root of 7. Okay. So of course we easily see that square root of 7 is between 2 and 3. Because 7 is between 4 and 9, so it is square root of 7 is between 2 and 3. So the integer part of this number, which is a0, as you can just guess, so that should be 2. So let's write square root of 7 as 2 plus x. 2 plus x. 2 plus x. Yeah. And then square both sides. So 7 is equal to 4 plus 4x plus x squared. So let's bring 4 to this side. So that is 3 equal to 7 minus 4 is 3 equal to 4 plus x into x. So x is, yeah, so x is equal to, oh, actually this is not a good idea. This is not a good idea. Let's not write it. Let's not square it. Let's not square it. Actually, it works for certain numbers. Like for square root of 6, this is going to work fine, but not for square root of 7. Square root of 7 is a little more complicated. So let's not do that. Let's write x in a way that we want. So put x equal to 1 over x1. So this is what we want to write. So x is 1 over x1 because we want it in that format. So 2 plus 1 by something, and that something is x1. So 7. So square root of so x is this. So square root of 7. Sorry. So this implies square root of 7 minus 2 is equal to 1 over x1. So what is x1? x1 is 1 over square root of 7 minus 2. So this is square. So I just rationalize the denominator. So square root of 7 plus 2 by 5. Oh, sorry, this is 4. This is 7 minus 4, so 3. So that is my x1. So that is my x1. So what we have done is written this as 2 plus 1 over x1, which is square root of 7 plus 2 by 3. Now we want to work with that number and write it as 1 plus 1 by something. So right now, so right now get an, or maybe just write put this number. So just start with the last number. So square root of 7 by 2 by plus 2 by 3 to be 1 plus 1 over x2. x1 is already used, so let's write x2. So if I do that, so I just subtract and then rationalize the denominator. So I would, just to be a little quicker, I would use my calculation and just write it down. So that what I got is 7 root square root of 1 square root of 7 plus 1 by 2. So if we go back to the beginning at the square root of 7, then what we have done so far is square root of 7 is now 2 plus 1 over 1 plus 1 plus 1 by square root of 7 plus 1 by 2. This is what we have done so far. So let's start with the last number x2. So put x2 equal to 1 over, so x2 is this number, so let me write it as, so yeah, we can write that. So x2 is 1 over x3, 1 plus 1 over x3. It is always 1 plus 1 over the next derivative, x3. So square root of 7 plus 1 by 2 is equal to 1 plus 1 over x3. Let me write, since I have the calculation, so let me write what my x3 is. So x3 is square root of 7 plus 1 by 3. But you would of course notice that the square root of 7 is just remaining. So isn't that very bad? So let's see. So that's not it. So square root of 7 plus 1 by 3. That's the last one we got. Yeah. Then we do the same thing. We would write one more iterate. So so x3, whatever we have so far is now written as 1 plus 1 over x4, and therefore this is square root of 7 plus 1 by 3 is equal to 1 plus 1 over x4.
So it's repeating.
It haven't repeated yet, but you are right. You are very much right. So this is just going to happen now. So just one more step. Yeah, that's the correct intuition. So as soon as it repeats, we are done. So that's why I said that even if we have the square root of 7 throughout, it's not so bad. It's exactly the point. So now x4, if you just calculate, this is 2 plus square root of 7. X4 is 2 plus square root of 7. Yes. So now 2 plus square root of 7 is large. So it is because square root of 7 is more between 2 and 3. So 2 plus square root of 7 is between 4 and 5. So we should write it as, okay, let's put 2 plus square root of 7 as 4 plus something. So something of this form. So then x5 is x5 is 1 over square root of 7 by 2. So I haven't cleared the I haven't rationalized the denominator because of the pattern. So this is what exactly is happening. The repetition comes now. So you can see here that x1 this is exactly, so square root of 7 minus 2 is exactly 1 over 1 over x1. So 1 by x1 is exactly square root of 7 minus 2. So this is what we have got. So this is just x1. So x5 is exactly x1. So there the pattern repeats. So what we have got by doing this is that square root of 7. Just let's try to write that. So square root of 7. We started with the 2, so this much I have written. So I would just write it down. I'm just using the calculation that we have done. So 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 4. 4. So 1, 1, 1, 4. Yeah. And then what happens? It starts repeating from here. So it exactly now 1 by 1 plus so etc. So again it is for it just repeats 1, 1, 1, 4. So it will keep repeating like this, 3 1s and a 4, because x5 is exactly x1. So the continued fraction expansion in that notation, what we have written down earlier is 2, 1, 1, 1, 4, and we put a recurrence on this. So this is going to repeat. So this whole block 1, 1, 1, 4 is just going to repeat, and it's going to repeat infinitely often, because any finite continued fraction is a rational number. So this is going to repeat. So this is just like a recurring decimal. It's a recurring continued fraction. This 1, 1, 1, 4 will repeat. So, but that this can again be a coincidence. This can again be a coincidence that square root of 7 is somehow nice, and we have this kind of a repeating pattern. But we would see that for this kind of quadratic irrational, what we say quadratic irrational, so it's roots of quadratic equation, this is going to happen. And but we need to develop some theory to see all this. So for any square, for square root of any positive integer, you can try this. This is going to work. This will work, and for, of course, it can be even longer calculation, but it would end up giving you the continued fraction. Yeah. Okay. So much for the introduction. So we have calculated a continued fraction for a rational number as well as for a quadratic irrational. Now let's develop a bit of theory.
Professor, we have a question. I have a question.
Yeah, sure.
So, what is the motivation of this corresponding continued fraction?
Corresponding.
What is the motivation?
Motivation. Actually, there are many. One of the important motivation for number theories is the approximation. Actually, as somebody pointed out, is the approximation of irrationals by rationals. So even these approximations like pi, this universal constant pi, so that we approximate as 22 by 7, and but we have a series of approximation going closer and closer to pi. So those things can be found via continued fraction. So those actually come from continued fraction expansions of those numbers.
Fine.
Yeah, and even more interestingly, if you know a continued fraction expansion, then you know how fast these rationals converge to that number, to that irrational number or term. whatever irrational number you started with, you also know the rate of convergence, that how fast it can converge. So it gives you a lot of information about approximating rationals, approximating irrationals by rationals. So that's a major motivation. There are some more things actually I would try to at least mention, but this is going to be the focus of our discussion, that approximation of irrationals by rationals. Yeah, actually it's a very big topic on its own, this what is called Diaphone approximation. So this is just the beginning of that. Okay, let me yeah, so so as I said, we would just develop a bit of theory. So much of it will probably be just recalling things for you, might have already seen, but to fix the notations and bring everyone to the same stage, we would do that. So so if anything is not clear, please interrupt. Okay. So just for the reference, so I'll be following the classical book of this Hardy and Wright. So this is whether you can see. So this is the Hardy and Wright theory of numbers. So that's an absolute classic. It's an excellent book. So that's what I would be following. For most parts. And notations or everything would be from that book. So, okay. Yeah, so what we have seen, at least for the first example, is a finite continued fraction. Finite continued fraction. And this would always be written as A0, A1. In some places, it is written as A0 with a semicolon, A0 and a semicolon after that to separate it from the, to emphasize that the first one is the integral part. But so we won't do that. It doesn't really matter. So this is a finite continued fraction, and this is the notation. And what we are, the number what we have is this, that 1 plus 1 over. Sorry, I keep writing 1. A2 plus 1 over A3, etc. and so forth. Yeah.
So all the A's are non-zero, and then A. What about A not? I think.
Yeah. So to start with, actually, to start with, we can simply consider them as algebraic quantities. So like algebraic variables. So you don't need to assume anything to start with. You can think of them to be real numbers, at least to start with. Yeah, let's say non-zero real numbers. Let's say non-zero. A0, of course, can be 0. So yeah, maybe we should have this convention that A0 is greater than or equal to 0, and all others are actually they can be negative as well. So
all other A answers should be non-zero.
Yeah. So let's
but
say
A0 should be positive. Or non-zero.
Yeah. So yeah. So you can always say that. So this let's just keep just say that all others are ANs are non-zero for all n greater than or equal. So that should be enough of the assumption to start with. We'll specialize. Actually, we'll say that all of them are non-zero. But to start with, we don't need. Now, have a bit of a definition. we can just see that if we are starting with a continued fraction which is up to this capital N, then we can also write it as A0, A1 to an minus 1, small n, and then put a continued fraction in its place. So an to a capital N can be just here. So I can write these notations because I am allowing real numbers. And these things, sorry, I can write it like this, and so there are two notations, two names. So this A1, so A0, A1 to AN, this is called the nth convergence, and this is called nth partial quotient. And this part, the rest, an plus 1 to an, this is called nth complete quotient. Nth complete quotient. So these are the names we are going to use. So complete quotient and partial quotient. Now we define let's define this. Define a series of numbers Qn and Pn and Qn by so for in greater than equal to 0 for all whole numbers. So P naught is just A naught. So given a continued fraction, we are defining this. And P1 is A naught A1 plus 1. Pn is an Pn minus 1. So recursive definition, Pn minus 2 for all n greater than equal to 2, because we have already defined it for 0 and 1. So and then 2 onward, we use this start formula. And just similarly for Q naught, so Q naught starts with 1 and Q1 is A1. And then Qn is the same recursion actually, an Qn minus 1 plus Qn minus 2 for all n greater than equal to. Oh, 1 second. I made I just gave it a wrong name. So these are convergence. Sorry, this is a wrong name. These are called convergence. Sorry about confusion. So these are called nth convergence. And Yeah, I think the other one is called complete quotient. That is probably the correct. Let me still just check with this book. Want to use the same. Yeah, innate complete quotient. That naming is correct. That is correct. But these are convergent. So innate convergence. And so these are complete quotients, and partial quotients are these ANs. So ANs are called partial quotient. Let me just mention this. Okay, so let's keep this assumption for the time being till we modify. And ANs are called partial quotients. So the entries of the continued fraction are called partial quotients, and if we stop at nth stage, then it's called nth convergent. And the tail part, starting from an to a small n to a capital N, starting from any nth stage to the end, that continued fraction is called complete quotient. So yeah, let's stick to that. And then we have defined this Pn and Qn in recursively. Recursively, and what we want to prove is the following. So so let's write it as a proposition that if this is the continued fraction or just the innate convergent, we don't need to deal with the full thing. So this is the innate convergent. This is equal to Pn by Qn, where P and Q are defined as above. So this is the as we defined above. So this is the innate convergent. So this is proved by induction. So this is proved by induction. So if you assume that you know it for say n, and then how do we prove it for? So this is proved by induction. So let's just do the induction step. For n equal to 0 and n equal to 1, it will directly follow from the way it is defined. Yeah, because if you just look at A0, then it is just P0 and Q0, just by definition, P0 being A0 and Q0 being 1. P1 by Q1, just by the definition, is 1 plus, sorry, A0 plus 1 over A1. So that is the continued fraction of A0, A1. So for n equal to 1 and 2, it's obvious. And then we do induction. So induction. Induction on n. So suppose we know it for n minus n, and let's try to prove it for n plus 1. So suppose we know this. And what we want to start. So suppose this. Then let's start with A0, A1 to AN and add one more AN plus 1. So I can just modify the last part to write it as AN. So what I would do, so the last part is this 1 over an plus 1. This is exactly the last part. If I put this together. So in place of, if I write this in place of an, then what I would get is this continuous fraction. Now let's call that a naught. Sorry, a dash. Let's call that a in dash. Let's say that this is a in dash. So what I have now is so I have written this n plus 1 length continued fraction as an n length continued fraction, but the last one is a n dash. But we know this relation for all n. All let's write it like this: all m less than equal to n. So as soon as its length is less than equal to n, we know it. So here also the length is n, so we know it. And use that. Let me add a page. So let's use that. So let's start with that. A naught, a1 to a n plus 1 is a n minus 1, and the last one is the same but with a dash. So this is what we know is say pn dash to by qn dash. So here we are using the induction hypothesis. For n length we know. So for whatever continued fraction of n length we know. So then we use the recurrence relation. So this the nth component into the previous one. That's how this recurrence relation is defined. An then pn minus 1 plus pn minus 2, and exactly in similar fashion for qn. So let me use that. So n minus 1. So of course here an important observation is that the pn is going to be different. So that's why we wrote pn dash, but all previous ones are exactly same as the original continued fraction. Because they all use these ans, the partial quotients up to an minus 1, so they would all be the same. So these pn minus 1 and pn minus 2 are the same one that we have for the original continued fraction. So now an dash, again the same thing. So qn minus 1 plus qn minus 2. Hope I'm writing this correctly. Yeah. So and now an dash is an plus 1 over an plus 1. Let's use that. So an plus 1 over an plus 1, n plus 1, that's in the suffix, pn minus 1 plus pn minus 2 these are an plus 1, the exact same thing, qn minus 1 plus qn minus 2. So let's just multiply out. So what we get is an plus 1. Let's write that first. So an plus 1 is being multiplied with this an pn minus 1. So this is going to give you an plus, sorry, an pn minus 1 plus this will get multiplied with this Pn minus 2, and there would be a Pn minus 1 remaining. Similarly, denominator just replaces P by Q, An plus 1, An Qn minus 1 plus Qn minus 2 plus Qn minus 1. Now we use the recursion. So from the recursion relation, this is Pn. So this, whatever this whole thing in the bracket is Pn. So this is An plus 1 Pn plus Pn minus 1, and this is An plus 1 Qn, sorry, Qn plus Qn minus 1. And this is again using the recursion. So here we have already used recursive relation. And we use the recursive relation again to write. So this is just Pn plus 1 by Qn plus 1. So we conclude that the original fraction, that continued fraction that we started with of length n plus 1 is now written in this way. So now by induction we have the proposition. So let's so this book of Hardy and Wright lists all of these things as theorems, small theorems. Let me just do this. Yeah. So let's look at this. So let's look at. So this is proved. I'll just put a box. And let's look at this. Consider this is actually a very important relation. So Pn Qn minus 1 minus Pn minus 1 Qn. So if we just use the definition, so An Pn minus 1 plus Pn minus 2, that's Pn, multiplied by Qn minus 1, and minus keep Pn, let's keep Pn, but write down the recursion formula for Qn. So An Qn minus 1 plus Qn minus 2. So note that the first terms are just the same. An Pn minus 1 into Qn minus 1, and from the second term it's again the same thing. An into P minus 1 into Q minus 1. Therefore they cancel, and what we end up getting is Pn minus 2 Qn minus 1 minus Q. Let's write P first. So P n minus 1 Qn minus 2. in fact, we have written here the larger p first, so let's write it in that way. So we take out a negative -1, and then this is p to the n pn minus 1 qn minus 2, because we here the starting formula had the p has the larger suffix, so let's maintain that, so that we can again have recursion. Pn minus 2 qn. So that's the same thing as what we started with. P only that n has been replaced by n minus 1. So if we keep doing this, what we would get is the following. Yeah, sorry, I couldn't hear you.
N minus 1, sir, last one.
Yeah, of course. Thank you. This is n minus. Yeah, exactly. So if I continue in this way, then what I get is Pn Qn minus 1 minus Pn minus 1 Qn is equal to minus 1 to the n minus 1. So this is an important relation actually. So let's give it a number. We'll always refer to it by 1. And from here we can do quite a few interesting things. So first of all, if we divide both sides of 1 by qn minus 1, then what we get is Pn by Qn minus Pn minus 1 by Qn minus 1 is equal to minus 1 to the n minus 1 Qn minus 1. So this is also very useful, so we just give it a number. And now we derive a similar thing for not just for difference 1 but for difference 2. Let me do that. Yeah. So let's let's do that. So recall. So recall what we proved by induction. So we proved that An by, okay, not yet. You just have to recall the definition. So An is An P, so Pn is defined as An Pn minus 1 plus Pn minus 2 and An Qn minus 1 plus Qn minus 2. So these are just the definitions of Pn and Qn, the recursion relation. Just use the recursion relation. And if we cross multiply, then what we can write is just Pn Qn minus 1 Pn minus 1 Qn is equal to Pn minus 2 Qn minus exactly this, so Qn minus 2. So as I mentioned, we are just looking at the difference of 2. So this is what I'm trying to do now. So so now use the previous relation, the equation 1 that we have proved. So use 1 on this side, so use 1 on LHS. So LHS has this part. So Pn Qn minus 1 minus Pn minus 1 Qn. So use 1. So that gives us, let's write this, just flip the sides. Minus minus this, just flipping the side. So Pn Qn minus 2 is An, and then replace this by minus 1 power n minus 1. That is what we get from 1 n minus 1. Now just flip this again to get the larger suffix for P. Pn Qn minus 2 and Pn minus 2. So this is, and one more negative, one more minus 1. So let's write it as n. Now divide this Qn into Qn minus 2. So Pn by Qn minus Pn minus 2, sorry, n minus 2 by Qn minus 2 is equal to by this is An. This is A. Yeah, actually, A and Q together can be a bit confusing, but every book or paper uses this notations, that ANs for the partial quotients and QNs, Pn by Qn for the convergence. So we would stick to that. Yeah. So so this is a very similar relation as 2, but between Pn by Qn and Pn minus 2 by Qn minus 2. So we would also use this. It's called that 3 is already. Oh yeah, it's 3. So this is 3. And using this, we can have several conclusions. Okay. Oh, okay. So when should I stop?
Only 6:30.
Oh, okay. So it's already time actually.
Okay, no problem, sir.
Yeah, so I won't overshoot. So I mean, I already have over. So that's so let's stop. So I'm lecturing on Tuesday, right? So I'll just continue with this. And
Okay.
yeah, so Tuesday we would set up all these kind of theory required to do a little more. Yeah, I might need a little more. So let's see. And so anyway, so if you have any questions for today, you can ask. So in fact, there is a WhatsApp group. So if you have anything to ask or any suggestion, you can send it there. I'm also in that group. And that's an easy option.
Okay, sir. Thank you, sir.
So shall I stop sharing then? So I'll be sending this, whatever I write, I'll be sending, I'll just make it a PDF file and and see if there are some mistakes, I'll correct it and then send this file.
Okay, sir.
So I'm going to email it to Guru Shami and then you can share. So whatever I write, I'll share. And as I mentioned that I'll be mostly using this Hardy Wright's book, which is fairly standard. So you can always refer to that. So,
Okay, sir.
okay, yeah. So okay, I'll stop.